What is up, guys? This is Physics 2212 Lab 4 Circuits. Here's the table of contents. And starting it off with some key concepts, we have Kirchhoff's law, which states that the sum of all the electric potential differences around the loop is zero. And Kirchhoff's junction rule says that the total current going into a junction equals the total current out of the junction. So we can use this to find some values in the experiment we're about to do. Ohm's law states that the electric current through a conductor between 2 points is directly proportional to the voltage across 2 points, and we get these formulas from that. And last one, capacitance, is the ability of a component or circuit to collect and store energy in the form of an electrical charge. And we will use C equals QV for this one. And going over the procedure, we followed these, and they were pretty much split into parts. The first part is a pretty simple loop right here, and we made this in the lab and also performed it on the digital version. And our value, the predicted current, was supposed to be 0.0204 amps. My actual current, which I conducted in the lab, was 0.02. And when you reverse the ammeter, it is negative 0.02 because you're putting negative to positive and vice versa. Then the next part was an RC circuit, which was a little more involved. And this one, there were a bunch of predicted values and values that we had to come up with. And basically, going through this entire experiment, the resistance was calculated to be 48 ohms, 102 ohms, and the resistance in the ammeter and the wires were zero, which is good. And to show this, I have a fun little slideshow. In the lab, we connected all the components to pretty much get all the values that we needed to here. And it took us a little bit because we had to connect the batteries and use each single one of these wires to connect every single component. So it got messy at some points. And yeah, this was our final circuit, which was supposed to show this RC circuit, which, as you can see, you have a capacitor, a 10 ohm bulb, a 20 ohm bulb, one 9-volt battery, and a 200 millifarad capacitor. We connected all of these, we built the circuit, and got the values that I just told you before. There wasn't much to it. It was a pretty big circuit considering that each component needs to be connected by these two, or by each of these wires. These were our multimeters that we used, and some of them were actually, because as you can see, our measured reading was 0.01. If we shifted the wires a little bit, it would go to 0.02. So I'm not sure if the ammeters were just faulty or whatever, because a few of them were actually blown out, so we couldn't use them in the lab. Going back to the slideshow, what if we were doing this lab in real life? Well, we did, and use an actual ammeter instead of an ideal simulated ammeter. What's different about a real ammeter, and how would it have affected the circuits you hooked it up to? If you did this lab with a real circuit, or with real circuit components, access the virtual circuit. Sorry, yeah, I didn't mean to include that. But basically, see if you can determine how it behaved differently from the real ammeter that we used. Um, Obviously, in the simulator, everything is in ideal condition. In the lab, unfortunately, some of the ammeters were like blown, so we couldn't use those. And in real life, ammeters have resistance. And in what if we were doing this lab in real life, used a real battery to charge a capacitor? How quickly would our ideal model predict the capacitor to reach full charge? Um, Our ideal model says it almost charges instantaneously. Would this prediction happen in real life? It would not, just because real wires and real ammeters, they have resistance. Also, capacitors also have resistance. So it would not be charged instantaneously. It would take a little bit longer than ideal conditions. And that's it for this lab. Thank you.